Hello everyone, my name is Rijvi. I'm going to present our work titled Chhoyhopper, a Moving Target Defense with IPv6. Scanning and brute force password attacks are still very common. Different enterprises frequently report brute force password attacks, and these events are still increasing. These enterprises observe enormous number of attempts to retrieve their passwords. The scary part is, the attackers can just use brute force tools to make these attack events with a very little cost. Last but not the least, the usage of scanning tools can scan the entire IPv4 address space in just 10 minutes. So the brute force attacks for stealing passwords are increasing. Malicious actors want to watch us actively or passively. They try to get access into our system actively, or they just try to observe our activities in the internet passively. As we said earlier, there are tools to scan quickly and make brute force attacks easily. Malicious actors do this scanning, which we can see in the background radiation data. Knowing sources and destinations, attackers can also observe passively to analyze traffic pattern to get sensitive information. Of course, with these known threats, people try to defend for a long time, but these defenses are imperfect. Defenders use various methods to defend these brute force attacks. They use except clause to restrict access only to known clients, but this method doesn't work when we have dynamic users. Port knocking is another technique where the legitimate users should knock in a predefined sequence of ports to get access into the system. The method works fine, but attackers may replay the same order after some observations. Closest to our work utilizes IPv6 address space for the security of IoT devices. We support today's popular SSH and HTTPS applications in this work. Our contribution is to propose a new idea to design a moving target defense using the huge IPv6 address space to defeat scanning and eavesdropping. We have deployed our system for SSH and HTTPS applications, and our solution is publicly available. Next, we describe our moving target defense and its components. Our new idea builds from two insights. First, if the service moves, then scanning and snooping won't be possible. Second, IPv6 address space is huge and we can try to utilize it. Based on these two insights, we propose Chhoyhopper, a moving target defense with IPv6. The word Chhoy comes from Bengali, which means the number 6 to represent IPv6. Our Chhoyhopper server moves in a known sequence based on current time and a secret key. Clients who know the secret key can only find out the moving address at a given time. From the moving figure, you can see that the happy client can connect to the service since they have the secret key. Here, the service is moving, but since legitimate client has the key, they can still connect. On the other hand, the adversary doesn't know the secret key, as a result, cannot find the moving address. Next, the obvious question is how the clients and the server find out the common address. As you can see from the figure, both the clients and the server rendezvous at a fixed address following a common technique. At first, the clients and server need to know the IPv6 address directly or using DNS. Then they generate a secret value based on the time, secret key, and the salt value. Then they replace the lower 64 bits of the IPv6 address using the generated 64 bits of secret value. We use a salt value to prevent the rainbow table attacks. We just saw that the clients and server need a secret key to converge. The next question is, how can they share the secret key? We assume the secret key is distributed out of band, which means the server admin and clients can share the secret key face-to-face or using email or instant messaging. Just like the way it works for SSH key sharing. We utilize the current time in minutes to generate the secret value. However, the client and server's clock might be slightly different because of clock drift. In our system, we listen on 2 addresses, each for 2 minutes with overlapping time slots. As a result, our current system can tolerate 60 seconds of clock drifts. So we are describing a system where service changes its address every minute and clients need to find out that address to connect. We don't want to change the clients and servers, and we want to keep Chhoyhopper transparent to users and clients. As a result, to keep Chhoyhopper transparent to users, we just tweak the connection setup of clients to find out the hopping address. Also, for server transparency, our server listens to a private address and we use NAT rules to translate the temporary address to the private fixed address. In that way, our server can run the service at a fixed internal address, which is transparent from our other use of external addresses. For stable connections, we use IP table state support to keep the already established connections. Till now, we have described our basic Chhoyhopper system. This core idea of Chhoyhopper is applicable for any applications. However, for HTTPS, we have some new challenges. The first challenge is transparency. SSH used command line interface, but for HTTPS, we need to use a web browser. Secondly, users want TLS authentication for HTTPS services. And here we are changing the IPv6 addresses. And getting a wildcard certificate for an IPv6 prefix is not possible. So we use the basic Chhoyhopper design for HTTPS for access control, but we need to solve these 2 challenges to run HTTPS successfully. We solve the transparency problem by developing a browser extension. Using the browser extension, a client can give inputs about the Chhoyhopper URL, secret key, and salt value. In this way, the client can give the required inputs. Then, whenever the browser finds a Chhoyhopper URL, it redirects the request to the hopping IPv6 address. We solve the TLS authentication problem by getting a TLS certificate for a wildcard domain name. We use dynamic DNS to provide a URL name for the hopping IPv6 address. Then, using the browser extension, only a legitimate client with the secret key can guess the hopping URL. Since dynamic DNS already adds an entry for the hopping URL name, the browser extension will get the right IPv6 address after the DNS resolution. Next, we show how our system works in real life. Our working system is publicly available for SSH and HTTPS applications. We show our real-life SSH implementation in this slide. The top figure in the black background shows logs from the server, and the bottom figure with white background shows how a client connects to the right IPv6 address. From the top figure, you can see that the server is listening at 2 IPv6 addresses ending with 9B99 and 11BA. From the bottom figure, we can see that the client and server rendezvous at the same IPv6 address ending with 11PA. In this way, clients and server converge to a single IPv6 address. In this slide, we show a real-life client-server interaction for HTTPS. The top figure with the black background represents the server log, and the bottom figure shows a screenshot from the client browser. As you can see from the top figure, the server is adding a new DNS entry with the hopping URL starting with 9AEF and the corresponding IPv6 address. The URL bar in the second figure shows how a client is redirected to the hopping URL starting with 9AEF to get the current IPv6 address to get the web page. We already show our system, its components, and how it works with real-life examples. Now, we want to evaluate two different types of risks. We want to explore the risk of discovery and the risk of collision. We fix a scanning speed with a specific packet size where we scan over a /64 prefix. We measure how much time it would take to find out a hopping address. We provide the detailed calculation in our paper. Secondly, we want to find out the risk of collision. Here we assume there are multiple servers under the same /64 prefix. Assuming there are 1 million servers, we calculate the risk of collision solving the birthday problem. We show the risk of discovery and collision here. We find that the expected discovery time is 3,000 years. And after this 3,000 years, the attackers would get only 2 minutes to conduct the brute force attack. In terms of collision, we expect a collision once in every 70 years when we have 1 million servers under a /64 prefix. So in summary, we can tell that the risk of discovery and collision is very, very low, and we can safely use Chhoyhopper without any discovery and collision. In this work, we developed a moving target defense by utilizing the huge IPv6 address space to mitigate scanning and brute force attacks. Our implementation is publicly available for SSH and HTTPS applications. Please try it out if you run such services. Thank you all.